Hi everyone, Mr. Ang here. So this is chapter 10 on sound, which is a continuation of the previous chapter on waves. So let's start by looking at what actually is sound. So in this section, we are going to understand how sound is produced and also describe the nature of sound waves as well as how they are transmitted. So sound waves are actually a longitudinal wave traveling in the air created by a vibrating source. So as we saw in the previous section on waves, we have transverse waves where the motion of the particles are perpendicular to the direction of the wave travel, as well as longitudinal waves where the particles are oscillating back and forth in the same direction that the wave is traveling in. So you can see here in this diagram, we have the particles, they are oscillating left and right in the same direction that sound is traveling. So over here, there are some of the particles which are marked out in red for easy reference, and this is really just to show that the sound wave is transmitting energy without transmitting mass, just like every other wave. You will also notice, in addition, you can see very clear wave fronts, and these wave fronts where all the particles are clustered together, these are called compressions. And in between the compressions, where the particles are very far apart, they are called rarefactions. So how does actually sound get transmitted through the air? It's because, when an object vibrates, what is going to happen is the air particles near the object will vibrate as well as the object collides into the air particles, and then the air particles will collide with their neighbors and thus transmit the sound energy, through this longitudinal wave. So as you can see over here, normally air is uniformly dense. That means that there is an equal number of particles per unit volume on average. However, once the speaker starts vibrating, it will start to push or pull, and that will result in compressions, as you can see over here, where a lot of particles are together, as well as rarefactions, where the particles are far apart. So in a compression, because the particles are very close together, the pressure is actually higher. So you can see over here on this pressure distance graph, there's a higher pressure. And in a rarefaction, where the particles are very far apart, then you have a region of lower pressure. So compressions and rarefactions are what define a longitudinal wave instead of the crests and the troughs. So in a longitudinal wave, we do not call this a crest, we call this a compression. We don't call this a trough, we call it a rarefaction. Now over here, you still see a displacement distance graph. So why is there a displacement distance graph? That is because, we are plotting the displacement of the individual particles relative to their normal equilibrium position before the sound wave. So in a compression, you will see that the particles, they are all pushed towards the compression. So particles before the compression get pushed towards, so they have a positive displacement, whereas particles after have a negative displacement as they are pushed in the other direction as well. In a rarefaction, the same thing happens, just in the opposite direction. The particles before, they are moving away, so they have a negative displacement, and the particles after, they have a positive displacement, so they move away from the rarefaction. And just like the transverse waves that we saw in the previous parts, this is periodic. So it repeats, and of course, if we have a displacement time graph, that would also repeat over time. So similar to our transverse wave, the wavelength is the distance between the successive compressions or the successive rarefactions. So very, very similar to the crests and the troughs. So that's a quick summary of what we've seen. Sound is a longitudinal wave which propagates as a series of compressions and rarefactions, and sound is produced by a vibrating source which requires a medium, because without the medium, you do not have particles to displace and therefore bump into each other and transmit this energy in the form of a longitudinal wave. So as you can see over here, sound cannot travel through a vacuum. So a common example is actually using a bell jar and putting a alarm inside and then slowly removing the air from the bell jar using a vacuum pump. As the air gets removed, the sound produced by the alarm in the bell jar will gradually get softer and softer until almost all the air is pumped out, leaving very few particles within the bell jar to collide and transmit the sound, and then you will get an almost silent alarm ringing inside. Once the air is pumped back in, then the sound will resume. However, the whole time, okay, this alarm is ringing, it's vibrating, okay, but because there is no medium, sound cannot be transferred. So this is actually very similar to conduction and convection. Those also do require a medium to transfer the energy, but instead of the collision or the movement of particles to transfer internal energy, what is happening here is sound, okay, is the vibration through longitudinal waves instead. So in general, okay, the speed of sound in solids is greater than that in liquids, which is greater than that in gas. So looking at our kinetic particle theory, okay, we can actually have a very easy way of understanding why this happens. So if you recall our kinetic particle theory, we will understand that in solids, the particles are packed very tightly together with very strong attractive forces. So what that means is when we have a vibrating source, the particles will react to that very quickly due to the very strong forces. And because they're very tightly packed together, the collisions will happen very, very quickly. And that is why the speed of sound in solids is very great. In liquids, okay, it's also very large. So for example, the speed of sound in water is almost 5 times the speed of sound in air, but it's a little bit slower because in liquids the particles are a little bit further apart, and because they are free to slide across each other, the vibrations may not be transmitted as well as in solids. However, it's still transmitted a lot better than in gases. In a liquid, okay, the sounds can be very clear even for hundreds or even hundreds of meters or kilometers. In a gas, however, okay, sound can rapidly taper off, and that is because the particles are very far apart. So the collisions may not always occur in a very nice and neat manner, which is why that sound in gases do not travel that quickly compared to liquids or solids. So here we have a worked example, okay, and over here, our first worked example asks us to label the regions of rarefactions with R. So to remember, okay, how to remember it is rarefactions. Maybe you can see the word rare inside, and that tells you that the particles are far apart. They have very low concentration or very low pressure, and that is why we have two rarefactions here, okay, where the air particles are very far apart. I've not labeled the compressions, but I think it's quite clear that there are three compressions within this figure here. So how does the air pressure at the rarefaction compare to the atmospheric pressure? Of course, it will be lower because the particles are further apart. And finally, the displacement distance graph. The principle is what I explained earlier. So if you need a recap on that, please go back to the earlier slides, okay, and reread the or re-listen to the explanation on why the displacements are like this, where near a compression they are positive before, negative after, and near a rarefaction they are negative before and positive after. So in the second worked example, we want to describe how sound travels through air from the speaker here to point A, and then in part B, explain why it cannot be heard if this setup was placed in space. So for part A, we know that sound has to be generated by a vibrating object, so in this case a speaker, so it either oscillates or vibrates, both are acceptable terms, and it collides with the air particles nearby. This would cause the air particles nearby to oscillate, which will then collide with their neighboring air particles and transmit the sound by causing compressions and rarefactions to be formed. Why the sound not exist in space? Why can't it be transmitted or heard in space? That is because there are no air particles and the speaker cannot collide with them to transmit the sound. Without any air particles, you won't have compressions, you won't have rarefactions. So in this third worked example, you want to label the compressions and rarefactions. So I think it's quite straightforward to do so. You can see the compressions are where the gas particles are compressed and close together, rarefactions where they are far apart. So calculate the wavelength of the sound wave. So if you look at it, okay, the wavelength would be 2.5 centimeters. And to state how the speed of sound will change if the medium is in water would be what we spoke about earlier, which is that the speed of sound would be much faster in water. So how do we relate loudness to amplitude and pitch to frequency? That is the next part of our chapter. So loudness is related to the amplitude of a sound wave. So recall from the previous parts that the amplitude is the magnitude of the maximum displacement. So the larger the amplitude, the louder the sound. So sound A over here would be louder than sound B. Okay, and this is what happens in the air as well. Very loud sounds will move the air particles a lot and also create regions of very high and very low pressure compared to the normal atmospheric pressure. So both in terms of the displacement of the particles as well as the change in pressure, the louder these are, the larger the amplitude of those, the louder the sound will be, because that will create a larger transfer of energy. As for pitch, okay, pitch is related to the frequency of the sound wave. The higher the frequency, the higher the pitch of the sound. So for those of you who play musical instruments, okay, you will find that the higher your notes are, the more quickly the string, or perhaps more quickly the air particles will vibrate. So depending on whatever instrument you play, whatever is vibrating, the higher the pitch, the higher that frequency in which the instrument or the part of the instrument that is vibrating is doing so. So over here, we will see that sound B has a higher pitch compared to sound A because it has a higher frequency. There are more periods per unit time, or each period takes a shorter amount of time, so more frequent oscillations. Now, looking back at our amplitude as well, these two sounds would be equally loud because both of them have the same amplitude, which is the magnitude of the maximum displacement from the equilibrium. Okay, so the human range of hearing is from 20 hertz to 20,000 hertz or 20 kilohertz. So frequencies below this are called infrasound. Frequencies above this range are called ultrasound. So ultrasound, okay, you might be familiar with this term, does have some extra applications, and we will talk about them, okay, in the next few slides. So now let's look at the worked example. Okay, based on sounds A and B and the pressure time graph, state which represents a louder sound. So based on this, I think it's very clear B is the louder sound because it has a larger amplitude or the larger maximum pressure difference. State if region X is a region of compression or rarefaction. Looking at X having a higher pressure than equilibrium, this tells us that the particles are close together and therefore this must be a compression. Now draw a sound wave with the same loudness as A but a higher pitch here. So this is what it's going to look like. Okay, pardon the pretty messy drawing, but you see over here the same loudness because it's the same magnitude. Okay, you can see over here 2 units, and it has a higher pitch because it has a higher frequency. There are more periods packed into each unit time. So how is sound useful? What are the applications of sound? Besides the obvious, which is how you're listening to this video, okay, we also use sound in producing echoes and how we can use these echoes for measuring distance, as well as what I mentioned earlier in ultrasound. So an echo is formed when sound is reflected off a surface, such as a wall, okay, and we use echoes to find the speed of sound in air. So for example, if we know the distance between two objects, a speaker and a very solid object that will reflect the sound, we can then use, okay, the time delay between playing a sound and detecting the echo in order to find out the speed of sound in air. Of course, we don't always need to use an echo for this, but this can be a very precise manner. And the other application, of course, of echoes is to determine the distance itself. So something that students might confuse themselves with or make a mistake about is forgetting that because an echo is a reflection, the sound has to travel to the object and reflect back. So the distance, okay, it travels is 2D, and therefore, okay, when you calculate the velocity of the sound or when you calculate the time taken, okay, you must take note of the fact that it has reflected back and traveled twice the distance between the speaker and the object it reflects off. So echolocation is a method in which some animals like bats, okay, can figure out the distances to objects. In fact, that is how they detect obstacles and hunt it at night when they are nocturnal and very active. So the delay between the emission of the sound and receiving the echo tells the bat the distance it is. And with its very complex and sophisticated ears, is able to also figure out the direction in which the echo comes from and therefore pinpoint the location of its prey or the obstacle. Besides bats, I believe dolphins as well as some other marine animals also use echolocation as a way of hunting or searching for prey. And you will remember that because sound travels much faster and much better in liquids, marine animals actually have a larger range when they do echolocation because the sound will be able to travel faster and further and still reflect back, giving them a very good picture of the surroundings rather than compared to their vision, because in water, light does not travel very well compared to sound. So human usage is sonar technologies. So fishing boats often use a sonar, and what it does is it emits an ultrasonic pulse and listens for the reflection. And after processing it, it is able to tell the fisherman where a school of fish are. Well, any single individual fish may not be a very good reflector of the sound wave. When you have a school of fish, the collective reflection and the collective echo, okay, would create a good enough picture to allow them to figure out roughly how deep they need to put their nets or what location they're in, and if they need to move on or find a better location where there are more fish. Of course, besides fishing, okay, submarines also use sonar in order to locate other submarines or other obstacles. However, this use of sonar would also give their position away because the sonar will be very loud and other ships would be able to detect, okay, where the submarine that is giving off the sonar pulses is. So another common technology is the reverse sensor of cars. As a car reverses, okay, many cars nowadays they have a model where there is a ultrasonic sensor which would detect the echo between the car as well as the wall behind it. So these obstacles, okay, would reflect the sound, and that time delay would allow the sensor to figure out what the distance is between itself as well as whatever obstacle is behind in order to warn the driver that you're getting very, very close to whatever obstacle it is, whether it's another car or a wall or a pillar, okay? And in more sophisticated car models, it's not just behind, but you will see in all directions as well. And this helps drivers to better park and navigate tight spaces. So, worked example, okay, if sound travels at 330 meters per second in air, and a boy makes a loud noise and hears an echo from a cliff face 1.5 seconds later, what is the distance between the boy and the cliff face? So the important thing to remember is because an echo has to travel to the cliff face and then come back, the actual time taken for the sound to travel is half that of the delay. So only 0.75 seconds, that is the time taken for the sound to travel to the cliff face. And then the other 0.75 seconds is for it to return to the buoy. And then using our ideas of velocity being distance over time, or in this case, distance being speed multiplied by the time taken, we are able to find, therefore, the distance is the speed of sound multiplied by the time taken for the sound to travel to the cliff face, which would then give us, 248 meters to 3 SF. Now for our next worked example, a fishing boat sends out a pulse of sound waves towards the seabed and picks up two echoes, a faint one followed by a strong one. Now, before I even go on to the question, why would the shoal of fish, give off a faint echo while the seabed gives off a strong echo? Now, this has to do entirely with what the composition is. The fish is not just solid, but there's also a lot of liquid and it's soft. And because it's soft, it doesn't reflect sound very well. That is why if you want to soundproof a place, you might want to pad the ceilings and the walls and the surfaces around so as to absorb sound rather than reflect it, or transmit it to the outside world. The seabed, however, is probably very solid and therefore would reflect sound very well, and that's why it has a strong echo. So the echoes are heard at 0.5 and 0.7 seconds after the pulse is emitted, and we have the velocity of sound in seawater being 1,500 meters per second. So to calculate the distance between the boat and the shoal of fish, the same method is used. We divide the time taken by 2 because it only takes 0.25 seconds to reach the shoal and then 0.25 seconds to return. Multiply that by the speed of sound in water and you will get 375 meters. So that's the end of this chapter on sound with our worked examples. If you require a little bit more time, please feel free to rewatch the sections of the videos which you might need some more help with.